Can you guys hear me now?
Yes.
Okay, sorry, I didn't have the mic plugged in. I was wondering why it wasn't working. Okay. I have one little issue that I have this morning. I forgot to bring my computer plug, so I hope that the battery lasts long enough for my computer. I do have a sub, but I don't know if it's delivering enough power to my computer. So if the power goes out, I mean, I'll let you know if the power goes, well, if the power goes out, we'll be done with the lecture. Seems to be doing okay so far. Okay. This next couple of days, we're going to be covering chapter 28. And exam 3 is on the 29th. It's going to cover chapters 26 through 28. So you have a couple of weeks to get ready for, almost 2 weeks to get ready for it. Okay. So I hope the class overall does better than the previous 2 exams. So today what I want to do is talk about simple DC circuits, and we'll get started on Kirchhoff's laws today too. Okay. I wanted to show you a video before I get started. I ended up the other day talking about, or last Wednesday, talking about the basics of circuits. And one of the things I need to talk about regarding working with electricity is the dangers of working with electricity. There's a handout on a module. I hope you got a chance to read it. It's called The Fatal Current. And it describes in it basically the amount of current that's required to go through your body to kill you. And it's about 75 milliamps. If you can get 75 milliamps through your body of DC current, essentially that will kill you, okay? Because it gets your heart to defibrillate. To fibrillate, sorry. Okay? And so this is essentially all you need. It's important to be careful working around electricity. Our labs are designed so that we're working with very low voltages and also very low currents, but we're working very low voltages, so it's going to be impossible to get electrocuted on these labs. Okay, so you don't have to worry about that with the experiments you're doing this semester. But as you go on, if you're an electrical engineer, you're going to be working with more dangerous voltages, and you got to be cognizant of the fact that you have to deal with safety issues. You don't want, for example, if you're working on something, you don't want the current to go through this way because that's going to go through your heart. It's probably a good idea to have one arm behind your back anytime you're working around electricity. You also want to don't work around electricity electrical systems by yourself. You want someone to be around you, just in case. Okay. Anyway, when the current's running through your body, if you have microcurrents running through your body you probably won't sense it. We actually do a lab on campus where we run current through our bodies, and basically we measure a body resistance and we calculate how much voltage you have to apply to your body to kill you. That's one of the labs we do in Physics 110. It's just a fun lab. Okay. It turns out when you start getting the milliamps range, you start sensing the current. I don't know if anyone's felt what it's like having electricity go through your body, but as a little kid, kids used to take the 9-volt batteries and put it on their tongue, put the electrodes on their tongue, and you feel the current going through on your tongue. If you ever, I don't know if anybody's ever done that, but as kids, we were curious about that, so we'd play around with that. It doesn't hurt, but you feel the sensation. And that's in the milliamp range. And as you get higher and higher in the milliamp range, your muscles will start contracting and then you won't be able to let go if you're touching a wire. You need someone to disconnect the circuit so you can let go of the wire. Okay. As you approach 1 amp, going through your body, your heart will actually stop. You're actually more likely to survive something that's 1 amp or higher than 75 milliamps. And the only problem with when you get to 1 amp is you start heating up, you start cooking. And so I want to show you a demo, not with a real person, it's with a hot dog. And I'm having trouble with the cursor here. Just give me a second, I gotta find the video. Tyler put together a nice video for us.
Experimental demos.
Hold on a second.
In front of you.
So Tyler put together a demo for us, and I want to show you this video. It's not that one. Not sure why I can't find it in my... For some reason my camera software will not allow me to show you the video. I don't know why. Okay, I'm going to try one more time and then I'm going to give up. Okay, I'm going to try it. Here we go. Oh, I know what I can do.
Experimental demos. In front of you, we have the dangers of electricity. There is a hot dog made to represent your finger, or you.
Okay, hold on a second.
And which will be running electricity or current through. On the left is a variac, so I'm going to adjust the AC voltage up, and we're going to measure it on the left.
Okay, it's working now.
In amps, and the voltage on the right. So if we follow this, the current, it goes through.
Can you folks
and
see
it's done
it?
in series, and the voltage is measured in parallel across them.
Yeah, it was frozen, but it's moving now.
Okay.
So we're going to turn it on. Keep adjusting it. 40 volts. I'm already getting almost 2 amps of current. I can see the top of the hot dog already bulging out. It's broken apart. And we have lots of steam.
Notice that current's over 2 amps. And notice how fast it started cooking. Okay. Anyway, you folks get the idea. Anyway, you folks get the idea of what it's like. I mean, if you get a significant amount of current through you, it'll basically start cooking you. Okay. Right. So I just want to show you that. Sorry it took me a long time to get that working. All right, so I want to talk about simple DC circuits. Basically, series and parallel circuits. I want to develop some basic concepts and basic equations involving simple DC circuits. So I want to consider 2 resistors in series. I want to have I'm going to have a power supply, resistor 1, resistor 2, I'll call this R1, R2, and my power supply voltage. And when I analyze this circuit, and really what I want to do is replace these 2 resistors with a single one that for which the battery provides or the power supply provides the same current. So the electrons going to go like this through the circuit. The number of electrons that go through R2 is going to be the same as the number of electrons that go through R1 because the electrons have no other path to go. They only have one path they go around. They have to go around this direction. Okay? And as they go in this direction, as they go through the resistors, obviously they're going to lose their energy. And these resistors might warm up. It just depends on how fast they can dissipate that energy. Okay, so the current through R1 and the current through R2 are the same. But what about the voltage drops? Let's think about the voltage drop across each resistor and how it's related to V sub S. Just to make it simple, I'm going to just put some numbers in. Let's say this power supply voltage is 3 volts. That means this point is at 3 volts. Let's make this a ground. Let's make this 0 volts. This point is at 0 volts. If you have current going through I should make these electrons, sorry. If you have current going through these resistors, that means there's an electric field in here. There's a voltage drop across each one of the resistors. And if the resistors are different, that means this is going to be at some intermediate value we'll call V. And this voltage drop plus this voltage drop has to be equal to delta V sub S. The current through each resistor is the same. We know from Ohm's law, the voltage drop across R1 is I times R1, and the voltage drop across R2 is I times R2. And so this is going to be equal to I times R1 plus R2. But like I said before, I want to replace these two resistors with a single one that yields the same results, the same current. You can see that the I's cancel, and so that the equivalent resistance is R1 plus R2. Questions on that? And that's pretty straightforward. I mean, it's like the capacitors in parallel. Okay, the resistors in series, they add like capacitors in parallel. All right. So whether you have 2, 3, 4, 5, 6, whatever resistors in series, you just add up their values. Now, what if you have resistors in parallel? That's going to be the next one. We're going to do the same thing we did with resistors as we did with capacitors. Now, I want to say, before I get to the resistors in parallel, I want to say something important. That if you go around this circuit, you go from 3 to a lower voltage, and then from a lower voltage to 0, and then from 0 to a higher voltage. If you add up all the delta V's in your loop, a drop, and then if you're going clockwise, you go drop, drop, and then gain. The sum of the voltage drops is going to be 0. In any loop, that's got to be the case. And the reason why is because this has to be true. Because the electric field is conservative. So that the integral of the electric field around the loop is 0. And so if you sum the voltage drops around the loop, you get 0. And this is going to be important later on today. Okay, and this is called Kirchhoff's loop rule or Kirchhoff's voltage law. You see it given those two names. Okay. All right, let's look at resistors in parallel. Let me draw a circuit. What's different about this circuit as compared to the series case? What's different here?
Is it something other than the obvious series versus parallel arrangement of the resistors?
Well, what about the voltage? The voltage drop across each resistor in this particular case. You know, we'll do our little. We'll put numbers in here. Down here, all these are 0 volts. So the voltage drop across each resistor is the same in parallel. I mean, that's the main difference. In the series case, they add. Here, they're the same. And then what about the currents? What happens to the electrons when they reach this point?
They have a path to choose.
That's right, they have a path to choose. More will go towards the path of the least resistance, right? For whichever one of these two are, I mean, if this one is less, more current will go through here than here. So you have two paths here. So the current here, we'll call this I, will split into I1 and I2, such that I is I1 plus I2. And this is actually an important idea. This is actually, you'll see in the next slide, one of the slides coming up. This is Kirchhoff's current rule. Okay, which is going to allow us to solve more complicated circuits. So the current from the battery is equal to the current through R1 plus the current through R2. But the voltages the voltage drops are the same. And so I1 using Ohm's law is delta V sub S over R1, and I2 is delta V sub S over R2. And again, I want to replace these two with a single resistor such that the battery provides the same current. And again, you can cancel delta V sub S's, and you get 1 over R equivalent is 1 over R1 plus 1 over R2. And in general, 1 over R equivalent is 1 over R1 plus 1 over R2 plus 1 over R3 plus dot, dot, dot. They combine like capacitors in series. Okay? Resistors in parallel combine like capacitors in series. Just give me a second here. Okay. So for resistors in parallel, the sum of the currents going into this junction equals the sum of the currents coming out. Or another way to write it is that the sum of the currents into any junction is 0. You can say that the sum of the currents going in is positive, those going out are negative. So the sum of the currents at any junction is equal to 0. Or you can say the amount of current that goes in is equal to the amount of current that comes out. And this is called Kirchhoff's junction rule or Kirchhoff's current law. And so we're going to use the two laws to solve more complicated circuits. So here's a review for resistors in series and resistors in parallel. Okay. And so what I want to do is, basically I want to do the same things I did for capacitors. I want to do a more complicated circuit and analyze it. So I'm going to put this on the screen, the whole screen. I want to look at this circuit. I want to find the equivalent resistance of the circuit. And I want to find the current through each resistor, the voltage across resistor, and the power dissipated by each resistor. Everything I need to know. So what's the first thing I should do?
You could simplify the two, or find the equivalent of the two 12 kilo ohm resistors on the right side that are in series.
So they add, right? So 12 plus 12 is 24, correct? And so I redraw my circuit. Now what?
You can simplify the circuits in parallel.
Okay, so I can simplify the 8 and the 24, so we got to do a little bit of math. The 8 and the 24, let's see. 1 over 8 ohms, that's kilo ohms, sorry. Plus 1 over 24 kilo ohms. Common denominator is 24, right? So if I take the reciprocal, what's 24 over 4? What's 24 divided by 4?
6.
Okay, 6 kilo ohms. So that we can replace those two resistors in parallel with a 6 kilo ohm resistor. And so I redraw the circuit again. Then those three are in series. And I just add them up. 5 plus 6 is 11, 11 plus 9 is 20. So now I have 20 kilo ohm resistors. So my equivalent resistance, my equivalent resistance is 20 kilo ohms. How much current do I have going through that 20 kilo ohm resistance? Well, I take 10 volts divided by 20 kilo ohms. It's going to be 10 over 20 is a half, but it's a half a milliamp. So I have a half a milliamp. Oops. A half a milliamp going through that resistor. I can also calculate the power. I can take voltage times current. If I take half a milliamp, which is 0.0005 amps times 10, give me 5 milliwatts, 0.005 watts. Now that 20 kilo ohm resistor replace 3 that are in series. Each one of those resistors has the same current going through them, half a milliamp. So the 5 kilo ohm resistor, 5 times a half is 2.5. It's going to have 2.5 volts across it. The 6 kilo ohm resistor is going to have 3 volts across it. And the 9 kilo ohm resistor is going to have 4.5 volts across it. And you add those 3 green values, and you get 10 volts. And then you do voltage times current, and you get the power dissipated. And if you add them all up, they better add up to the 5 milliamps. Now, I have some round-off issues there, but those 3 values will add up to the 5 milliwatts, which is the energy delivered by the battery. Now, remember, we're going backwards now with the circuit. So that 6 kilo ohm resistor replaced an 8 ohm and a 24 kilo ohm resistor that were in parallel. And since they were in parallel, the 2 resistors have to have the same voltage across them. And now we can figure out the current through them, because all I got to do is take 3 over 8,000, which will give you 0.125 milliamps. And then the other one will be 3 over 24,000. I'm sorry, I said that wrong. 3 over 8,000 is 0.375 milliamps. 3 over 24,000 is 0.125 milliamps. I rounded them off in the figure. You add them up, you get half a milliamp. And again, you can calculate the power. Delta V times I, or I squared R, or delta V squared over R. That 24 kilo ohm resistor replaced 2 resistors that were in series. They replaced two 12 kilo ohm resistors. Since those two resistors were in series, they're both going to have the same 0.12 milliamps across it. And they're each going to have half the voltage because they're the same resistor. So they're each going to have 1.5 volts. If you take the 0.12 amps times the resistance value, you'll get 1.5 volts. And so I have everything I need to know regarding the circuit. You solve these circuits much like you did the capacitor circuits in the previous homework assignments, except that your equations are different. Okay, so before we go on, I want to do a quick demo with some light bulbs. So let me set up my demo here. I have this board, this big board, and I can ask you guys some questions about series and parallel. Okay. Let me zoom in on this thing. I have 3 light bulbs here. Can you see the bulbs? If I tilt it like this? Okay. 25 watt bulb, a 60 watt bulb, and a 200 watt bulb. I'm going to give the system, I'm going to give some juice to the system. I'm going to give it some power. Which bulb will be the brightest? The 25, the 60, or the 200 watt bulb? That's my question, you guys. Any guesses?
Are they all going to be the same?
The same brightness?
Well, the wattage is a function of current and voltage.
Let me write the power equation down. Maybe that'll help. Let's see.
You zoomed in, so we can't see that.
Oh, it's too far up? Okay, sorry. I'll write here then. Can you see those? Kind of. Hold on a second.
Yeah, they're on screen.
Okay. So having said that now, having those equations there, I guess which one's going to be the brightest?
Would it be the 200 watt bulb?
Anybody else?
Does the direction of current matter for this?
Does it go whether it goes this way or that way?
Yeah,
Are you saying does the order matter?
I guess. Yeah.
Okay. We can try that. Should I turn it on then? Can you see this one is lit?
Oh, just barely.
Barely. And that one's not at all, right? Why is this one the brightest?
It's the first in the series, and it's consuming a lot of the current with its resistance and not leaving much left afterwards.
Okay, so let me, I'm going to switch them. The connections are kind of loose on this thing. I'm kind of worried. All right, so I switched them in this circuit. Did it make a difference?
Huh. What do you know?
Yeah, Huh is right.
Or order doesn't matter, right? Remember, they all get the same current, don't they?
Yeah.
Okay, so they all get the same current. So that means the voltage drop across each one is I times R. Which one is going to have the biggest voltage drop if they have the same current? It's going to be the one with the biggest resistance. Which one has the biggest resistance?
The lowest watt bulb.
Yeah, so that one has the biggest resistance. It's going to have the biggest voltage across it. Okay, because remember, these bulbs are rated at 120 volts. None of them are getting 120 volts. They're getting something less. And this one's operating closest to it, the 120. But now, what if I put them in parallel? Well, I have a loose wire here somewhere, hopefully. Oh, this goes here. The 60 might not light up. I have a loose wire in the back, so. Now what's going to happen? Now which one's the brightest?
Well, unless you have a way of bridging those two circuits that you just broke.
Oh, so I got to do this then. Right? Hold on a second. Can you tell the top one's the brightest? I don't want to look at it because I'm going to go blind.
I think so. Its
Okay.
its bloom is a little larger than the one below it.
Yeah. So, and the reason why is they're all getting 120 in that case. Each one of these, because they're in parallel, they're all getting the full 120. When they're in series, they're not. Okay, when they're in series, the voltage they're getting is based on this equation. They all have the same current through them, but the one with the biggest resistance has the biggest voltage drop. Okay, so let me put 325s in series. Let me take this out. Okay, let me take this out. I like the 25s because they're not super bright. Okay, so these are 325s in series. Can you see that they're lit?
Yeah, all about the same.
They're about the same, right? They have the same current through them. They have the same rating. So, okay, so suppose, I'm going to put it up here because this one's disconnected. Suppose I put the 60 watt bulb here. What's going to happen?
The 60 watt has less resistance, so the one that's in the middle of the series right now will probably dim, but the two on the sides might stay the same.
Okay, let's try that.
Or brighten. I think they might brighten.
You're right, they brighten. You know why? Because these two are in parallel. So if you take two resistors, they're in parallel, their value, the value of the equivalent resistance is lower than either one of these two resistance values. So you have three resistors in series. This resistance is lower than either one of these two. These have the same resistance, so they're going to have the same voltage drop across them. This will have something less. That's why it goes out. I mean, it's not even glowing at all. Does that make sense?
So the resistance is lower because the bulbs are hooked in parallel.
Yes.
Is that what you're saying? Okay.
Yeah. Those two bulbs are connected in. These two bulbs are connected in parallel. So just like we did for the, are you able to see that? Oh, you can't see that. When we did the 24 kilo ohm resistance and the 8 kilo ohm resistance, we combined them and we got 6 kilo ohms. The resultant was lower than either of the two resistors. So you combine these two, the resultant is lower than either of these two resistance values.
Okay, gotcha.
Okay, and so now we have a lower resistor, lower voltage drop, because really these two, the combination of these two is in series with these other two.
So why did our the lower of the two middle bulbs, why did that go out if the resistance is lower?
Why did this one go out?
No, the one below.
Oh, why did this one? Well,
Yeah.
these are combined. These are in parallel, right? They're combined.
Is it because our current is lower across them?
The current is the same. The equivalent resistance is lower. Let me draw the circuit. This is what the circuit looks like. Okay? When I combine these two together into one, all right, these two, the behavior of these two is the same as, I'm running out of space. This replaces these two. So the voltage drop across this is going to be equal to the voltage drop across either one of these two. The current through this one is the sum of the currents through either one of these two. In fact, this will have more current going through it than this one.
And because of the current drop when we added the fourth bulb, there's no longer enough power being delivered to keep that one lit.
There's not enough voltage drop across this resistor to get it to glow. Yeah, there's not enough power dissipated to make it glow. You're right. You can say it that way. There's not enough power delivered to this one to make it glow. That's because you put that one in parallel. If I take it out, then all that current that was going through here now goes through here. So you're diverting the current. It's not getting all that current anymore. And so so you get less power delivered to this bulb than before. Does that make sense?
Just barely. But yeah.
You have to play around with the numbers. It's a little bit more difficult with the light bulbs as opposed to just resistors because they're all rated at 120 volts. Okay, and then the one with the bigger resistance is the one with the lower wattage rating. That's one of the issues with doing the bulbs. Okay. So like I said, when I put this in parallel, now the equivalent resistance of these two is lower. It's the same thing as if I took, what I just did is the same thing as if I took this 200 watt bulb and put it here. Same effect. Okay. This is the same effect as having those two in parallel. This bulb is not getting enough energy delivered to it to make it glow. I squared R is lower. You might want to go through this video several times, and that'll help you sink in, and then maybe play around with the numbers, and you'll get to see it, that it makes sense. Okay. To me, this is a very instructive demo because, you know, most students will say what you guys said, you know, the order matters, but it doesn't. Right? The order does not matter at all when they're in series. Okay? Because each one's getting the same current. Okay. Anyway, I just wanted to show you this demo. And if you have more questions about it, you can email me. Also, in the conceptual questions for this unit, there's a bunch of bulb questions too, and you can try answering those. If you can conceptually understand what's going on in this system, then you're going to be fine with this unit. Okay. The next problem I want to do and I think to me it's a fairly important problem because it's your lab. Or not the problem, but the circuit. This circuit is essentially the lab you're going to be working on. The DC circuit analysis. So I'm going to spend a little bit of time analyzing this circuit. And in the past, it had a very practical applications because it was used to measure resistance, to precisely measure resistance. All right, so let me draw this. This is a diamond shape circuit. Let's call this R sub A. R sub B, R sub C, and R sub D. And I'm going to hook this up to a power supply.
Professor,
Yeah.
we can't see the top of the...
Okay. I forgot to, thank you. I'm zoomed in too much, that's why. Okay, can you see it okay now?
Yeah.
Is it better?
Yeah, it is.
Okay. All right, there's our power supply voltage. So first question I want to ask, can I find the right combination of resistors so that if I put a device here to measure current, I get 0. I want 0 current through this ammeter. Of course, the answer is yes, I can find the right combination of resistors, but how do I do that? How do I find the right combinations of resistors so that I get no current through that ammeter? Well, what does it mean that I get no current through the ammeter? It means all the current goes, so it means the following. Power supply delivers current here, and it splits this way and this way. Current goes like this. None of it goes through the ammeter. So you have the current go through here and the current go through here, completely ignoring the ammeter. And if that's the case, then what can you say about these two resistors? Are they in series or parallel?
Would they be in series?
Yeah, because there's no current going through here, right? These two resistors are in series, and these two resistors are in series. Basically, I have this circuit. And if you don't like the way that I drew them, I could still draw it like this. Doesn't matter. I can draw it like this. That's essentially what I have. But I have no current going from here to here. But this is drawing it like this might actually make the analysis a little bit more difficult. So if there's no current going this way or this way, what does that mean?
Would that mean that the overall resistance on the two side paths would be less than the resistance of the ammeter?
Well, let's pretend the ammeter is ideal. It has no resistance at all. What can you say about the potential here and the potential here?
They would need to be the same.
They're the same. So the voltage drop between these 2 points and the voltage drop between these 2 points is the same. So I can say that the current through A times R sub A, and doing it this way, see, when I redraw it this way, it kind of messes up my analysis, is equal to I sub B, R sub B. And of course, then the voltage drop between these two has got to be, the voltage drop between these 2 points has to be the same as the voltage drop between these 2 points. But since these two are in series, these currents are the same. Since these two are in series, these two are the same. Let's divide the equations. So if the resistors match these ratios, then you'll get no current through here. And many years ago, they used this. This is called a Wheatstone Bridge. They use this to measure resistance. What you would do is you choose a set value for A and B. This would be your unknown. And then C would be a value would vary. So this would be these two would be set resistors. This would be a variable resistor. It would be a box or a wire whose length you can change depending on what kind of precision you're looking for. And this would be the unknown. And you just vary this value until the current's zero in here. That's an old experiment. We generally don't do that anymore, but that's the Wheatstone Bridge. Okay. We okay with that?
So R sub A doesn't mean that it's inversely related to R sub C.
Well, no, because if I multiply both sides by R sub C, I get all right, so it's not inversely related. It's inversely related to R sub, let's see. Right, I mean, R sub C is in the numerator here, right? If I solve for R sub A, or if I solve for R sub C in terms of R sub A, if this gets bigger, that gets bigger. It is inversely related to R sub D.
So all we have to have is those ratios to be equal to each other.
Yeah,
Is
that's all I need.
Hmm.
So there's a lot of different combination of resistors that'll cause it to work. But as long as they match this ratio, then you're fine. You get no current through here. So what if there's current going through there? So in the lab, you're going to be looking at this circuit, but it's not going to be a balanced bridge. In the lab, what you're going to do is you're going to have this circuit. You're going to do one case where you just have this, and you're making the measurement, and then the same circuit, you're going to put a meter across here and do the same analysis.
This will be in the DC circuits lab.
Yeah, this will be the DC circuits lab. This is the setup for the DC circuits lab. So the first part, what you're going to do is you're really testing Kirchhoff's laws. You're going to be measuring the current from the power supply. We're not going to have you measure the current everywhere because it's really a pain to do with one ammeter, okay? And it's easy to blow fuse. And so we're going to have you measure the current out here. And the way you're going to measure the current here is by measuring the voltage drop across this guy and the voltage drop across this guy. So the voltage drop divided by R sub A gives you the current. Does that make sense? So you're going to be measuring it indirectly. You're going to be using Ohm's law. Voltage drop divided by R sub A gives you I sub A. Voltage drop across R sub B over R sub B gives you the current. And the sum of these two has to be equal to this. And so that's what you're trying to prove in the lab. Does it make sense? Okay. So let's say let's choose some values for R sub A and V. So let's put some values in. Let's make this 300 volts. Let's make this 3 kilo ohms. Make this 6 kilo ohms. I want to put a meter here. And I want to measure the current through the meter. Now, when I put the meter there, I am forcing points 1 and 2 to be at the same potential. Okay. But with the Wheatstone Bridge, I want the potential difference between 1 and 2 to be 0, even without the meter there. So how do I solve this circuit?
Would we start by finding an equivalent for the top and bottom halves since they're in parallel?
Yeah, these two are in parallel now, right? I mean, really, the circuit I have looks like this. That's essentially what I have. Now, if I replace these two with a single one, a 2 and a 2, 1.5 plus 1/2 is what? 1? One half plus 1/2 is 1, so this is 1 kilo ohm. For this one, 1/3 and 1/6 would be 2/6 plus 1/6 is 3/6. This is 2 kilo ohm. So I have 300 volts going through it. What's my total current? Well, I can redraw my circuit again. And so I have 100 milliamps of current here, 3 divided by 3,000. So these two have 100 milliamps across it. How many volts across each one of those? Well, 0.1 amps times 2,000 is 200 volts. So these two, which are in parallel, are equivalent to this guy. How much current through each one of these? 100 divided by 2,000. 100 divided by 2,000, what is that? 0.05 amps, 50 milliamps. Now what about this one? 200 volts. 200 divided by 3,000. Right, 200 divided by 3,000. There's 200 volts here. $200 divided by 3,000 is 66 milliamps. 200 divided by 6,000. So let me go back to this circuit. I have 66 milliamps going this way. I have 33 milliamps going that way. Over here I have 50 milliamps. And over here I have 50 milliamps. So what must be going through here? I have 66 coming in, 50 coming out. How much is going that way? Actually, this is 67. It's 66.66, whatever. If I have 67 going this way, 50 coming out, how much is going that way? What's 67 minus 50?
17.
17. is 16.7, but whatever. And so I guess 17 milliamps going this way, 33 milliamps going this way. What's 33 plus 17? 50. In the second part of your lab, you're going to set up this circuit. You're going to actually have the meter here the entire time. Now, my analysis assumes that the multimeter has 0 resistance. What about in your case?
I don't think it can measure without resistance.
I'm sorry?
I don't think it can measure without having resistance, so there has to be resistance in it.
There is a
I don't know what that
resistance.
is.
It's small, but you're right. It's there, right? So in your case, I'm going to have you do this for 2 different current settings to show you the effect the resistance has on the circuit. The resistance of the ammeter has on the circuit. Okay, so you're going to do the second part twice. You'll have this connected here, and you're going to be measuring this voltage drop, this voltage drop, this voltage drop, and this voltage drop, and you're going to test Kirchhoff's current rule. You're going to see the current. The current going through here is equal to this current plus that current. The current here is going to be equal to this current plus this current. Okay, what is the effect of this guy as compared to part 1? Look at the effect of putting this here as compared to part 1. Okay, just by putting that measuring instrument there, I want you to see the difference between part 1 and part 2. Now, the actual physical measurements that you're going to make are easy because you're going to measure this voltage, this voltage, this voltage, this voltage, and the current through here. So you're making like 5 measurements. And then the other case, you're going to make 6 measurements because you're going to have this meter here. And really, that's it. It's the analysis that you have to do with the air propagation that's really long. Okay. In terms of doing the experiment, it's actually easy. But writing it up is going to take you a while. Okay? Questions on this problem? Because this is your lab. I've gone through then, so I've gone through and calculated all the values, all the I's and V's values for the circuit. One of the questions in the lab is to actually derive an equation for the resistance of, for the voltage across one of those resistors in terms of the other resistance values and the power supply voltage. Okay. I did this with the numbers, that you can do this very quickly, especially with nice numbers. I chose nice numbers. Questions on this? Okay, so Friday we'll talk a little bit more about the procedure, but this is the entire this is the circuit you'll be looking at. Okay. I want to look at this next circuit. Can you guys see that okay?
Yeah.
I want to calculate the current through the ammeter. This is a horrendously complicated circuit. You should take some time to draw it on a piece of paper, because I'm going to draw it on the board while you can't see the board. So just take some time to draw that. I'm going to try to make it a big drawing. Okay, so I drew the circuit. I want the current through the ammeter. This looks horrendous. Yeah, it's not easy. Just tracing it, and tracing the current is not easy. This is how I would do it. Okay, because some people are good at tracing the current. I will tell you, I'll be honest about it, I'm not. However, I can tell you where what the voltages are at different points in the circuit. So let's say this is 0 volts, and you can see it in the diagram. This is 100 volts. This point is at 100 volts. Now the ammeter is ideal, so the ammeter is not going to have any voltage drop across it. So this point's got to be 100 volts. There's no voltage drop across the ammeter, it has no resistance. So this point's at 0 volts. This point's at 0 volts. So if this is at 100 volts, and this is at 0 volts, what's the voltage drop across that resistor? It's 100 volts. Again, I is delta V over R. So the current is going to be 100 over 1,000. What's 100 over 1,000? It's 1/10 of an amp. What's the voltage drop across this resistor?
The same. 100.
So the current is going to be 0.1 amps, right? And the current across this one is 0.1 amps. I'm sorry, through that one. So each resistor has 0.1 amps going through it. Okay, so now what? This is at a higher potential, that's at a lower potential. So it would seem to me that, I wish I had more colors. I don't think green shows up very well. Current's going to go this way through this resistor, and the current's going to go this way through this resistor. It has to, because high potential, low potential. Current goes from high to low. Current goes from high to low. So you have 1.1 amps going this way, 0.1 amps coming that way. Where did it come from? It came from here. So that must have had 2.2 amps going through that meter. And you have, this is from high to low, you have 0.1 amp going this way. And so going through this wire, how much current is going to be going through this wire? You're going to have 0.2 amps going through this wire, and then 0.1 amps. So you're going to have 0.1 amps going this way, 0.2 amps going this way, and then down here you get 0.3 amps. Just by looking at the voltage drops and looking at Ohm's law. I couldn't do any series parallel thing here. But I used Ohm's law, and I used another law. What was the other law I used? Or rule? What's the other thing I used? I used the current rule. I used the current rule right here to get that. Study that circuit. It's not an easy circuit. So I want to say something about internal resistance, just a quick little thing. Most real power supplies have an internal resistance. And so we usually draw a real power supply with a box around it and a little r representing the resistor value. And here's our load resistor. Okay, I'll just call it R, but this is our load resistor. Could be a light bulb, could be whatever. Generally, you design your power supply is designed so that R is small. They're very small. It's actually hard to measure, okay, with a multimeter. A battery's internal resistance is not very small. In fact, it gets bigger as the battery gets older. Question is, oops. For what value of big R is the power delivered, I'm sorry, what value of little r is the energy delivered to the load maximized? When is the energy delivered to this guy maximized? It turns out when these two values are equal, the energy that's delivered to the load is maximized. How do I analyze this circuit? Well, basically I have two resistors in series, so my current, the power supply voltage is denoted by E, the EMF. Then my current is the power supply voltage divided by little r plus big R because they're two resistors in series. The voltage across the resistor is I times R, which is equal to E over R plus R times R. The power dissipated by the resistor is this times this. How do I maximize this? How do I find when it's maximized? Those of you who remember your calculus.
Take the derivative with respect to little r instead of equal to 0.
Yeah, actually, we want to find, yeah, I forgot, it's the big R. We want to find the value for which, the value of big R in which the power is maximized to it. So I'm actually going to take the derivative with big R. But it really shouldn't matter. It really shouldn't matter. I want this to be 0. All right, so let's take the derivative of this with respect to big R. I like writing it. I don't remember the quotient rule, so I write it this way. So I want this thing to be 0. And I'm going to find a common denominator. And I'm only concerned with the numerator. I don't care about the denominator. So basically I want which says that R minus big R equals 0. So little r equals big R. So the maximum energy, the energy that's transferred to the load is maximized when the internal resistance equals the load resistance. Now, have you ever turn the headlights on and then turn your car on? Have you ever done that before?
But I don't remember what happens.
So if you turn the headlights on and then turn the car on, the headlamps will dim. Because you're going to have, when you turn the car on, you have a lot of current going through this resistor. That's going to make this voltage drop a lot lower. You have a lot of current going through the internal resistor, giving it a significant voltage drop, and you'll see the headlamp get dimmer. Before I end, I know I'm a little bit over time. Questions: how are devices connected in your home? Series or parallel? How are things connected in your house? Think of the demo I did with the 3 light bulbs in series. I'm sorry, I didn't hear if somebody said something.
I was going to say, would it be parallel?
Yeah, they have to be parallel, because imagine, you saw what happened to the 200-watt bulb when I put it in series with the other bulbs, right? You didn't even see it go on. If you have everything in parallel, if you have your air conditioner in parallel with one of the light bulbs in your house, if you have your air conditioner in series with one of the light bulbs in your house, the air conditioner ain't going to work. You're going to have no voltage drop across the air conditioner. Okay, so the air conditioner needs its own.
I don't know why, but I thought about Christmas lights in the house. Sometimes they're in series, or they are in series, and how when one bulb goes out, and like a whole section of it.
Yeah, when one bulb goes out, either they all go out or a section goes out, right? The old ones, the whole darn thing would go out, but they wire them differently now. Yeah, everything in your home is in parallel, because otherwise you're not the devices won't get 120 or 240. Won't get the voltage that's needed to get them to operate. What about the circuit breaker? Is it in series or parallel?
Like the whole arrangement of circuits or an individual?
Well, circuit breaker is designed so that if you're drawing too much current, you trip it, and to protect your wiring, and power goes out. So how would you want the circuit breaker to be connected with the rest of everything in your house?
Be in series.
Yeah, in series, because
in between the source and the devices.
Yeah, so the circuit breaker goes out, you want everything else to go out. So the circuit breaker has to be in series. In the old days, it was a fuse. What's the purpose of the grounding prong on your socket and on the plug?
Keep me from dying when something goes wrong.
That's right. In the old days, things like washers and dryers didn't have the grounding prong. And so when you had a problem with the short, if you touched the body of the washer or dryer, you get killed. The grounding prong then allows the current that on the body of the washer, if you have a short, it goes straight to ground. It won't go through you, because the currents wants to go where there's a lower resistance. I'm trying not to say the current takes a path of least resistance, because students get confused by that. But more current will go in the path where you have a lower resistance, so you won't get killed by it. And then what happens to the internal resistance of a battery as it ages, it gets higher. Okay, I think I'm going to stop here because I'm a little bit over. So next time, I'm going to get into Kirchhoff's laws. This problem kind of hints at Kirchhoff's laws. So I'm going to stop here. Questions? No questions? Oh, let me check the chat. Okay, you're welcome. All right, so I'll see you guys on Wednesday. And go ahead and rewatch the video with the demo if you had a hard time with it.